Hello students, welcome to my lecture series on reinforced concrete structures. In this class, I am going to discuss about step-by-step procedure for a design of one-way slab. This design with respect to demonstrated method as per IS 456-2000. So let us see what are the outcomes of today's class. After completion of this class, you will be able to know what are the step-by-step procedure for a design of one-way slabs, and after knowing the steps you will be able to design by your own a simply supported one-way slab. So let us recall the points what we discussed in previous class. We have discussed about definition of slab, classification of slabs, and design requirements of a slab as per IS 456-2000. So let me brief what is a slab is. A slab is a two-dimensional structural element which is used as a flooring as well as a roof covering. In this slab, our load distribution will be taking place by a bending action, and these slabs are classified as two groups based on their longer span to the shorter span ratio and based on the support condition. So based on their longer span to the shorter span ratio, if that ratio is less than or equal to 2, the slab is categorized as two-way slab. If the ratio is that Ly by, I can say the longer span is Ly, the shorter span is Lx, Ly by Lx is greater than 2, then that slab is categorized as a one-way slab. Right? In one-way slab and two, what is basic difference? In one-way slab, the reinforcement, that is the main reinforcement provided in shorter direction, that is only one direction, and the two-way slab, the reinforcement provided in both the direction, both the directional reinforcement are main reinforcement. We can treat it as a main reinforcement, that is a shorter direction as well as a longer direction. And then we have discussed what is the design requirements of a slab as per IS 456-2000. So first of all, we have to have some requirement for the effective span of the slab. You know that effective span can be calculated based on the two conditions, and one condition is a center to, for if you take the simply supported beam, that is first condition is a center to center distance between the supports, or I can say the supporting wall. Another condition is clear span plus effective depth. By using these two conditions, we can calculate what is the effective span of the simply supported slab is, and we can consider the minimum of these two value as a effective span for the particular simply supported slab. Then we have to have a limiting stiffness, or I can say deflection. To deflection control, we should use some L by D ratio. The L by D ratio is given different type of beams at different values. So that L by D ratio is for cantilever beam it is 7. So for simply supported beam it is 20. For continuous beam it is 26. It is given in your IS 456-2000 class number 23.2 of IS 456, and it is for spans not exceeding 10 meters, right? And then we have discussed another requirement of a design of this particular one-way slab or any two-way slab also, that is the minimum reinforcement, the main reinforcement should not be less than, that is 0.15% of gross cross-sectional area when you are using a mild steel. If you are using HYSD bar as a main reinforcement, then the minimum area of reinforcement should not be less than 0.12% of gross cross-sectional area. Then coming to the important aspects of this design requirement is a maximum diameter of a bar. In no case the maximum diameter of a bar should not be more than 1/8 of thickness of the slab. So that is, remember this point, in no case the diameter of a main reinforcement should not be more than 1/8 of thickness of the slab, right? So that condition, that requirement has to satisfy while designing these slabs. Then we have discussed spacing of main reinforcement and distribution reinforcement also. The maximum spacing allowed is 3 times effective depth of the slab or 300 mm, whichever is less for the main reinforcement. For a distribution reinforcement, that is 5 times D, that is 5 times effective depth, or 450 mm, whichever is less. And one more requirement also we have discussed, that is regarding a cover. That cover should be satisfied, that is nominal cover provided in the slab, that will be provided in the sides of slab, above the slab and below the slab, right? That means below the bottom reinforcement, above the top reinforcement, and side reinforcement also. That is based on table number 16 of IS 456-2000. The size of the cover, concrete cover, will depend upon the exposure conditions. So these are the things we have discussed in previous classes. By knowing the knowledge of these design steps and design requirements, we'll have some design step for today's class, that is, say, the step-by-step design procedure for one-way slab. So in order to design the one-way slab, you need to follow these steps, then only it will be very easy to you. So first of all, we have to calculate what is the effective span is. This effective span can be calculated according to the clause number 22.2 of IS 456-2000. There we may design as a one-way slab, a simply supported slab, or a cantilever slab, right? For if you are using a simply supported slab, the effective span will be considered as between the below mentioned two conditions, that is a clear span plus effective depth of the slab. Another condition is center to center distance between the support. So the value obtained from these two conditions, the minimum value of A and B will be taken as a effective span for a simply supported slab. If you are designing a one-way cantilever slab, here also we have two criteria, that is A and B. A is a clear span plus effective depth of the slab, or the depth of the slab I can say, and second one is a clear span plus half of the support width. Clear span plus half of the support width. So we'll take the effective span for this cantilever slab as minimum of criteria A and criteria B. So this is how we calculate effective span for different type of beams and different kind of criteria like this. Then second step would be calculation of effective depth. So here we have to assume a suitable effective depth based on the stiffness criteria. You know what the stiffness criteria is. So just now we have discussed, stiffness, limiting stiffness, there will be some basic values. So that is L by D ratio, it is called it as a, will give the basic value for different category of beam. So effective depth of a slab can be calculated, that is span by basic value multiplied by modification factor. Here this basic value can be obtained by based on the type of beam, and modification factor we have to assume, and span already we have calculated, that is generally we can take as effective span in our previous step. So this formula is derived like L by D is equal to basic value, from that D is equal to span by basic value actually, but this basic value must be multiplied with a modification factor. You can choose this one, or directly you can choose a effective depth of a slab from this condition, that is span to depth ratio may be selected in the range of 25 to 30 for simply supported slabs. Okay, you can choose a ratio of L by D in between these two also, or otherwise the span and basic value for simply supported beam, and consider any modification factor as assumed. If now it is assumed, then when we are discussing about a check against a deflection, then we can check whether this modification factor is sufficient or not. There we can decide. You can follow this step, you can follow this step, that is you can follow this point or this point. First point is span by basic value into modification factor. From this you can take the effective depth, or you can assume span to depth ratio may be selected as in the range of 25 to 30 for simply supported beam. Once you know that L by D equal to say 25, from that D equal to L by 25, that will L value already known to you. From that we can calculate, that is assumed effective depth of a slab, right? Then we have to calculate loads. So load can be calculated by considering 1 meter width of the slab. We cannot consider here whole width of the slab. We will calculate by considering 1 meter width of the slab. So generally we have different kinds of load like dead load, live load, or any superimposed, that any finishes are there, those loads all we have to calculate and we add together. Finally we calculate what is the total load is. Generally your dead load will be the self weight of the slab or floor finish. So this can be calculated overall depth by unit length by unit weight multiplied by unit weight of the RCC. So you know the unit weight of RCC and you know unit length that 1 and D is the overall depth. How to calculate this overall depth? Overall depth can be calculated effective depth plus effective cover. Overall depth equal to effective depth plus effective cover. From that we can calculate what is the overall depth is. And then we will provide you in the problem or a design live load or it can be also call it as a superimposed load on slab. This is conforming to IS 875 part 2. Now after knowing the total dead load and total live load, we have to calculate what is the total load is. Total load is equal to dead load plus live load. From this we can calculate a factored load. So this the combination of load or dead load and live load. For this we are designing a slab. It is a flexure member. It may be tends to bend. So we have to design it with respect to limit state of collapse in flexure condition. In limit state of collapse in flexure condition, the partial factor of safety used for combination of dead load and live load is 1.5. So your total load must be multiplied with a 1.5. Then we'll get what is the factor load or factor design load or ultimate load we can say. Right. After calculating that, we have to calculate what is the design moments. So based on the ultimate load or a design load, we can calculate what is the design moment, or I can say it is ultimate moments. So here we have two different cases for different type of beams. Say for a simply supported beam with uniformly distributed load, that is WU, is acting over a beam. This from that we can calculate what is the ultimate moment is, ultimate bending moment is, that is mu equal to WL square by H. So this formula you can obtain from your previous concepts from shear force and bending moment from the subject called strength of material. There when a simply supported beam subjected to UDL throughout, then we'll get the maximum bending moment or ultimate bending moment at the midspan, that is WL square by 8. In place of W we have a factor load, that is WU. So by using this formula we can calculate what is the design moment is. Then if you are designing a cantilever beam, it is subjected to uniformly distributed load W, then the design moments for cantilever beam is mu equal to MUL square by 2. From this formula we can calculate what is the design moment for cantilever beam subjected to UDL. Right. After calculating design moments, we have to calculate limiting moment of resistance. This limiting moment of resistance can be calculated from these formulas. These formulas given as for IS 456 2000. This formula will depends upon the grade of steel. So for Fe250 it will be 0.148 FCK BD square. For Fe415 it will be 0.138 FCK BD square, and Fe500 it is 0.133 FCK BD square. Right. Let us check or let us calculate what is for given dimension and given data of designing the slab, what is the minimum depth required or what is the minimum effective depth required for resisting the maximum bending moment. For this we have to equate limiting moment of resistance with a maximum moment bending moment or a factored bending moment. With this, then we'll get mu is equal to mu limit. So this discard this root, the root is not there. And after effective depth required, D is equal to under root of mu by K into FCKB. Right. Here K is the some factor that is depends upon the grade of steel. So for the Fe250 it is 0.148 and Fe415 it is 0.138 and Fe500 it is 0.133. So after substituting value of K and given grade of concrete and 1 meter width of the slab, then we can calculate what is the effective depth of the slab is. Right. So if the calculated depth or the minimum depth required is a less than the depth assumed earlier, whatever for second step is less than the assumed depth is more than this calculated minimum effective depth, then we go ahead with the further steps. So then our slab will bear the maximum bending moment also what is coming onto this. So from this I can say if the effective depth required is less, required depth is this calculated depth, less than the provided. Provided means what we assumed earlier. Use provided depth and go for a further step. When this value is provided depth is more than the required depth, then we can adapt a provided depth and go for the further steps for a further calculation of design of a slab. So next we have to calculate the area of steel per meter width of slab by using given formula. As we know, any design, it may be a beam or a column. A design means calculation of its dimensions and amount of steel required in the particular RC element. Similarly, we have decided what depth to be provided for the slab, one way slab. Now we have to decide what is the amount of steel required for a meter width of slab. So that can be calculated with respect to the moment of resistance formula, mu equal to 0.87 Fy AST into D into 1 minus Fy AST by FCK BD. Right, if you substitute the values like AST, Fy, FCK, you know AST is area of steel required, Fy is the yield strength of a steel, FCK is characteristic strength of a concrete. Right, if substitute here, we'll get what is the AST is. Generally from this equation we'll get a equation in the form of quadratic equation. So if you solve that quadratic equation, one positive factor will give you the what is the area of steel, or the minimum value will consider as a area of steel. After calculating area of steel, we have to go for checking minimum steel required. So as for design requirements of a slab, the minimum steel required for HYSD bar is 0.12% of gross cross-sectional area, and if you are using Fe250, that is 0.1% of gross cross-sectional area. Whether this obtained AST is fulfilling the criteria given in IS 456-2000 for a design of a slab, those we have to check. So after checking, if the minimum steel is less than the obtained steel, then we go ahead, or the minimum steel is more than the obtained steel, then we have to provide minimum steel reinforcement in the slab and go for the further steps. Okay, then next step we have is we have to calculate spacing of a main reinforcement. So we have to provide. Now we have decided what is the area of steel required. From that we can calculate what are the number of bars also. For that number of bars, what is the spacing to be maintained between the bars? That we have to calculate here. The spacing can be calculated by using this formula, that is S equal to AT by AST required whole into 1000. This 1000 is the unit width of the slab. Here AST is area of one bar and AST is required steel, and after calculating this ratio and multiplying with 1000, we will get what the spacing is. So after calculating spacing, we have to check the obtained spacing with the design requirement given by our IS 456-2000. What is the requirement given in IS 456-2000 for a slab? The spacing of main steel should not be more than 3D or 300 mm, whichever is less. Right. So for example, if you get a value here is more than this condition and this condition, the spacing which you obtained from your calculation is more than this 3D and this 300 mm. And after that you have to calculate 3D is somewhere 450. Which value you have to adapt it? This is more than this and this is more than this. And among these three, 1, 2 and 3, minimum value will be provided as a spacing for the bar. Right? But no case the spacing should not be more than these values, that is 300 mm or 3 into D value. Okay, right. Next we have to go for checking of distribution reinforcement. You know the distribution reinforcement in one way slab are provided along the longer span of the slab, that is in LY direction. There also we have to provide the reinforcement, but the reinforcement should be provided is minimum. That minimum is, if you are using Fe250 bar, then it will be 0.12%, and if you are using HYSD bar, if you are using Fe250 bars, then the area of distribution reinforcement is provided is 0.15% of total gross cross-sectional area, and if you are providing HYSD bars, then the area of reinforcement required as for a distribution reinforcement is 0.12% of gross cross-sectional area. And here also we have a spacing. The spacing can be calculated as usual. You have to assume some suitable diameter of bar. From this point you have to calculate what the actual spacing is, and that actual spacing will be check with the codal requirements. So what is the codal requirement given? The obtained value is should not be more than this 5 times d or 450, whichever is less, that value will be provided, right? So the maximum distribution still should not be more than, the spacing for the distribution still should not be more than 5d or 450 mm, whichever is less, right? Let us check after calculating after the amount of steel required and dimensions required for a slab, and what is how to process, what is the spacing for the steel reinforcement, and what is the number of bars required. Then we go for check whether designed slab with all those parameters will save against the deflection, or really it will restrict the deflection or not. That we have to check. That can be checked by using, after knowing the percentage of steel. The percentage of tension reinforcement can be calculated by 100 AST provided by BD, and calculating stress in steel under the service load, that is FS. It can be calculated like this: Fs equal to 0.58 Fy into AST required by AST provided. From this we will get Fs and PT, and here we have a graph given in your IS 456 2000. So for given particular percentage of steel, what is the modification factor we have to calculate, and this modification factor is corresponding to the percentage of steel as well as, and is Fs, where the Fs values are provided in the form of a graph. Say if you are getting say 0.4% of a steel, and if you have a 240 Newton for mm square is the Fs, then what will be the modification factor is, say here 0.4% of steel, 0.4% of steel, and 240 is the curve, that is Fs. Corresponding to this, I will calculate what is the modification factor is, and this modification factor is lying between 1.2 and 1.4. So I can assume it as a modification factor for this particular PT and Fs, that is 1.3. Like that we can calculate what is the modification factor. Finally, we have to check like this: your L by D maximum must be greater than L by D provided. What is the L by D maximum? L by D maximum means effective length to the effective depth. Maximum value will be calculated by multiplying basic value with the modification factor. So basic values are provided like this. If you are designing a simply supported beam, then the basic value will be 20. If you are designing a cantilever beam, it will be 7. If you are designing a continuous slab, then it will be 26. And KT will be, that is a modification factor will be obtained from this graph. If you multiply that, we will get what is L by D maximum. This L by D maximum must be greater than L by D provided. L by D provided means what? L is the effective length or effective span of the slab, and D is the effective depth provided. This value must be less than L by D max. Then we can say our slab is safe against the deflection. So this is all about design of a slab with respect to the limit state of collapse in flexure condition, and we can design it for shear also. So for shear check, we have to check it against the shear, whether it is resisting the shear force or not. So for that we have to calculate ultimate shear forces. This ultimate shear force depend upon the type of condition, loading condition, and type of support condition. So if you are designing a cantilever slab with uniformly distributed load, then the maximum shear force will be Vu equal to W into L. It is more or less similar to your beam only. And for a simply supported beam subjected to UDL throughout, the maximum shear force will occur at the support, that is V equal to WL by 2. And from this we have to calculate what is the nominal shear stress is. The nominal shear stress value can be calculated by using this formula, which is given in IS 456 2000 according to class number 40.1, that is tau V equal to Vu by BD. Here Vu is the factored shear force that we have calculated earlier, and B is the 1 meter width of the slab, and D is the effective depth of the slab. From that we can calculate what is the nominal shear stress tau V is. After calculating tau V, we have to calculate the maximum shear stress. The maximum shear stress in concrete can be calculated by using table number 20 of IS 456 2000. This maximum shear stress will depends upon the grade of concrete. Suppose your grade of concrete is M20, then tau C max is 2.8. So there is a condition that if tau V is less than tau C max by 2, then it is okay in shear. In addition to this condition, we have to check another condition also, that is with respect to design shear stress. So if the design shear stress Values, design shear strength values can be tau c value can be calculated. Table number 19 of IS 456 2000. So these are the AST provided, and this is grade of concrete given, and by using grade of concrete and AST provided, percentage of steel, we have to calculate what is the tau c is. After obtaining the tau c value, we have to compare this with our tau v. For the slab, this tau v must be less than or equal to k into tau c. Here k is some factor given with respect to some solid slabs for calculating shear strength of a concrete. Then according to the 40.2.11 class number, the k value can be calculated. So here this k value will depend upon the overall depth of the slab. If the overall depth of the slab is more than 300, then it will be used as a 1. It is 275, that is 1.05, 250, that is 1.1. Where, say, from this graph you can say, if the overall depth of slab decreasing, this k value will be increasing. Up to 150 or less, we can use 1.30. Right? From that we can calculate what is our value is, total shear strength capacity of a solid slab, that is k into tau c. Suppose your slab is 150 mm and tau c is, say, you can obtain from this is say 0.36. The tau c value will be 0.36 multiplied by 1.3. That this value, total factored value, must be greater than or equal to tau v. Then we can say our slab is safe against the shear. Generally, slabs are safe against the shear and its development length. In slabs, we will not separately design what is the shear reinforcement is to resist the shear force, but we will provide the shear reinforcement in the form of a bent up bars. As we are providing main bars in the slab at the shorter direction for one way slab, those bars are bent at the edges, that is 0.1 L, that is 0.1 into effective length times that will from the support face to the right side. For example, if you take the left support, and if you take the right support from face of the support to the left side, the distance will be is 0.1 times L. From the distance we have to bend those bars. So those bent up bars will act as a shear reinforcement for that. We have to bend a 50% in left support and 50% at right support to make it symmetric. Those are sufficient for resisting the shear forces which are coming onto the slab. There is no separate shear reinforcement designed for that. So hence, most of the cases we will not check shear and development length for the slab, but anyhow we are discussing here because the reinforcement are provided and bent up bars that we have provided, they are self-sufficient for resistance against the shear forces. So let us check for the development length of the bar. So development length is LD must be less than or equal to M1 by V into L0. So here LD is development length of the bar. It is a minimum length of the bar which is inserted or embedded into the support. That length must be less than equal to this value. That M1 is a bending moment intersection, that is with respect to the 0.87 Fy. That means the steel what we are provided, all steels must be stressed. That moment we have to consider, and V is the shear force of the section consider, and L0 is the sum of the anchorage length. This anchorage length generally depends upon the diameter of bar and angle of bend, right? This is all about your development length. It must be less than this, right? So these are the step-by-step design procedure for complete design of a one-way slab. So here we have one more design problem, that is given that a simply supported RCC slab has to be provided for a roof of a clear dimension 3 meter by 8 meter. So we can assume like this: there is a two supports over the slab is there. The slab is 3 meter by 8 meters. In this, LX is shorter direction, 3 meter is shorter direction, 8 meters is longer direction. Here I can call it as a LX and it is a LY. Width of a support wall is 300 mm. It is not the width, it is the width of the support wall is 300 mm. So we require this support width for calculating the effective span. And the weight of weathering course over the slab is 1 kilonewton for meter square. I can say it is a finishing load, that is 1 kilonewton for meter square. Take the live load on the slab as 2 kilonewton per meter square. That is imposed load, or I can say live load. Now design the slab using M20 grade concrete and HYSD steel bars and check the design for deflection only. So in this problem he has restricted up to the deflection. This does not mention check for remaining like shear and development length. So I will solve this problem up to deflection only. In next class we will design a complete one-way slab and with the aids of your design steps. Say with respect to the given data, we have to decide whether it is one-way slab or two-way slab. In the problem, nowhere it is mentioned that it is a one-way slab or two-way slab. But we know what is the shorter direction and what is the longer span or the longer direction of a slab. Based on that, we can decide whether it is a one-way slab or two-way slab. So let us say Lx is 3 meters and Ly is 8 meters. Now if the ratio of Ly by Lx is equal, that is Ly is longer span, that is 8, shorter span is 3, and the ratio of this is 2.67. Now this 2.67 value should be compared. It is greater than 2. We know that our fundamental definition of a one-way slab or two-way slab, if one-way Ly by Lx is greater than 2, then we can categorize it as a one-way slab. So with respect to this data, the slab obtained is Ly by Lx is greater than 2. So the slab designed as one-way slab. Right? We have decided that we have to design this slab as a one-way slab. So the given data is like that. Clear span is given, that is 3 meters. Wall thickness is that is the width of the wall is given 300 mm, and live load is 2 kilonewton per meter square, and weathering course given is 1 kilonewton per meter square, and as grade of concrete is M20, so the characteristic strength of a concrete is 20 newton per mm square, and yield strength of a steel is Fi equal to 415 newton per mm square. By using this data, we have to design a slab and we have to check with respect to deflection only. So let us start one by one step. We know the first step will be calculation of effective span. As we are designing in the problem, it is mentioned that the type of slab we have to design is a simply supported RCC slab. For simply supported RCC slab, the effective span can be calculated by using these two criteria, that is clear span plus effective depth of the slab. Right, the 3 meter plus effective depth of the slab, generally we have to take from this the effective depth of the consider. We can consider by using span by basic value into modification factor. The span is 3.12, right, and I'm assuming that is 20 is the basic value and 1.25 is the modification factor. From that I will get that is 120 mm, or how much? 120 mm is effective depth, and for that I am adapting clear cover is 20 mm and I am using 10 mm bars. So after 120 means I have to check whether when I am deciding the bar 10 mm, whether this bar is with respect to design requirement or not. What is the design requirement for the maximum diameter of bar? That is the maximum diameter of bar should not be more than 1/8 of thickness of the slab. That we have to check and we have to provide. So it is self-sufficient, that is 10 mm bar, and from that we can calculate that the overall total depth D equal to 20 plus that is Fi by 2. It is effective depth plus clear cover, 20 mm is a clear cover, plus half of the diameter of the bar, that will give the 145 mm is the overall depth. Right, I am assuming here from this condition the effective depth of the slab is 120 mm, that is 0.12. Say 3 plus 0.12 is 3.12 meters, and the center to center distributed support is 3 plus 0.3, that is 3.3. We can consider minimum of these two value as effective span for the simply supported slab. So what is the minimum value? That is 3.12 meter. Hence provide effective span as 3.12 meters. So then we have to calculate effective depth of, you can say, thickness of slab. We have calculated based on this formula, and that is a small d 120 mm and is the overall depth, that is 145 mm. Right. Then we have to calculate a load, that is the total load, or you can say design load or factored load. So here we have to consider 1 meter width of the slab. By using that we have to calculate what the dead load is. Dead load can be calculated overall depth of the slab multiplied by unit length and unit width of the slab multiplied by unit weight of RCC. So from that is the unit one, so I can neglect that. 0.145 into unit weight of the RCC is 25. Then the dead load will be 3.625 kilonewton per meter square, and live load given is 2 kilonewton per meter square. Here you may have a doubt that why it is taken in terms of meter square. As I told you at the definition of slab is a two-dimensional element. So for we are calculating the dead load for a unit area. Say for 1 meter area this will be the dead load. For 1 meter area live load. For 1 meter area this is a floor finish. Like that we are calculated. That's why per meter for meter square area we are calculating loads here with respect to slab. But with respect to your beam we have calculated load per meter length. Understood? You got the difference between the beams and slab for calculation of loads. For beams, we have calculated total load with respect to the per unit length. Here, we have to calculate the loads with respect to per meter square area. So, after calculating dead load, the live load is given in the problem, that is 2 kN per meter, and total load will be dead load plus live load for floor finish, that is given in the form of weathering course, that is 1 kN per meter square. That is for dead load it is 3.625 plus live load is 2 and plus floor finish is 1. Altogether we get total load is 6.625 kN per meter square. From this I can calculate as the factor load is. The factor load is, we are using combination of these two. Then the partial factor of safety for limit state of collapse condition is 1.5 into total load is 6.625. Then the total factor load will be obtained 9.938 kN per meter square. Then we have to calculate what is the design moments or ultimate moments. As we are designing the simply supported one-way slab, then the moment will be calculated with respect to this formula, mu equal to WL square by 8. Already we have calculated W is, that is 9.938 into L is 3.12 square by 8. So mu equal to 12.09 kilonewton into meter. So after calculating mu and by equating ultimate moment and the limiting moment of resistance in the section, we have to calculate what is the minimum depth required. So again please, this is a copy paste mistake. This root is not there. The formula will be mu equal to K into FCK into BD square. That from this D we can calculate D equal to under root of mu by K into FCK. K value depend upon the grade of steel. So as a substitute the values of mu, K, FCK and B. Here mu is 12.09 10 power 6 by FCK, that is FCK is 20 and B is 1 meter width, that is in terms of mm, 1000 mm, and K is a factor. In this design I am using Fe415C as a SYSD bar, that is 0.138 is the factor. So if you substitute all those values and you calculate, the effective depth required for given dimension is 66.2 mm, but we have assumed is 120 mm. So our provided depth is more than minimum depth required for the slab. So we can go ahead with a provided depth of effective depth of a slab. So by using that effective depth and by using Fy and bending moment what we calculated, from that we have to calculate what is the area of steel by considering 1 meter width of the slab. So this can be calculated by using this formula, mu equal to 0.87 Fy AST into D into 1 minus Fy AST by FCK into BD. So you know what is mu is, that is 12.09 into 10 power 6 is equal to 0.87 plus Fy is 415. AST we have to calculate, and effective depth of the slab is 120 of 1 minus 415 AST by FCK 20, B is 1000, D is 120. If we calculate that, we will get a quadratic equation like this. After solving this quadratic equation, we will get what is the AST is. AST equal to 294 mm square. Right? Then we go for check for minimum reinforcement. After calculating the total reinforcement required, whether the obtained reinforcement is sufficient or to satisfy the design requirement of a slab with respect to minimum reinforcement provided. So for Fe415 still we are using the minimum reinforcement required is 0.12% of BD. Here the 0.12% of BD, if we calculate the area AST minimum, that is 174 mm square is required minimum reinforcement, but obtained is 294. So your AST minimum is less than AST. So we can say that it fulfill the design requirement of a minimum reinforcement. So we have assumed that initially we have to use 10 mm diameter bars, and for that we have to calculate spacing of bars. We know how to calculate spacing of bar. S equal to AST by small AST by capital AST. Small AST is the area of 110 mm bar. AST is the area provided. Then and 1000 is the 1 meter width of the slab. From that we can calculate what is the spacing is. So spacing equal to AST by small AST by capital AST into 1000. S equal to small AST is 78.5 for 10 mm diameter, and 294 is the provided provided area of steel, multiplied by 1000 will get spacing is 267.1 mm. Now this obtained spacing should be checked with our codal requirements. So as per IS 456 2000, the for maximum spacing for main bars should not be more than these two conditions. That is, one is 360, 3D and 300 mm. For 3D means it is 360 mm. Among these two, whichever is less or obtained value is less, we can provide. So the obtained value is less than these two. So provide we can assume as a spacing between the main reinforcement is 267.1 mm. So it is rounded to 260 mm. So hence provide 10 mm bars at 260 mm center to center spacing. So as there is no shear requirement to resist the shear forces, we have to bend the 50% of bar in left hand support and 50% of bars in right hand support, so that the length of the bent bar should be 0.1 times L from the face of the support, either face of the support. Right, those like that we have to calculate alternate bent bars, that is 50% like in this direction and 50% in this direction. Those bars should be bent alternatively. Okay, right, this is how we calculate for main reinforcement. Then distribution reinforcement. So there is no particular design for distribution reinforcement. Distribution reinforcement should be provide minimum reinforcement. So as they are providing Fe415 steel, the minimum reinforcement should be provided is 0.12% of gross cross sectional area. For the AST minimum obtained is 174 mm square. But as I told you that our diameter of distribution bar should be less than diameter of main bar for a one-way slab. That's why I am assuming 8 mm diameter of bar, which is less than the main reinforcement. The spacing of our bar is S equal to AST by AST into 1000. AST, where small AST equal to 1 bar of 8 mm diameter. The area of that particular is 50.24 mm square. And if you substitute that, we'll get the spacing is small AST equal to 50.24, capital AST equal to 174 multiplied by 1 meter width. Then we get spacing is 288.8 mm. Again, this obtained value of spacing should be conformed with our design requirements. That should not be more than these values, or if it is more than these two conditions, then the minimum of these two value provided as a spacing for the distribution reinforcement. But according to this problem, we got a spacing is less than these two, so this value will be provided. So with respect to the criteria 5D, 5 into D, the spacing is 600, and another criteria is 450 mm. The obtained value is less than these two values. The spacing should be maintained for distribution bar is 280 mm center to center. Of a diameter of bar is 8 mm. Right. Then we go for checking of a deflection. As we know that checking of deflection should be with respect to the percentage of steel and your FS, that is stress in steel under the service loads. So percentage of steel can be calculated by 100 AST provided by BD. Say I am providing 294 AST is 100 is 294 by 1000. B is 1 meter width of the slab, D is effective depth of the slab, that is 120. According to this, I got the 0.252 percentage, and I want to calculate stress in steel under the service load. The formula will be Fs equal to 0.58 Fi, AST required by AST provided. This will be provided by S456 2000 also. From that, if you substitute the values of Fy and AST required and provided, we will get Fs equal to 240 kilonewton for mm square. By obtained percentage of steel and obtain Fs, we have to calculate what is the modification factor is from the graph provided here. This graph are also available in our S456. From there only I have copied this. Right. So for the for Fs equal to 240, Ft equal to 0.25, what will be the modification factor? Say direct curve is available, but here this is 0, it is a 0.4, between 0.2 is there. Just adjacent to the 0.2, we have a 0.25 percentage of steel. So approximately I am going here. See, here is the curve, and it will be it is intersecting at this point. The corresponding here, my modification factor is there. That means your value remains between the modification factor value remains between 1.4 to 1.6. So approximately I am choosing the modification factor value is 1.4 for this particular case of Fs and Pt. So according to this Fs, Pt and modification factor value, we have to calculate L by D maximum, that is my basic value multiplied by Kt, as we are designing simply supported beam. For basic value for simply supported beam is 20 and Kt is 1.5, that is equal to 30. L by D provided is, that is effective length by effective depth, that is effective length is 3120 and by effective depth is 120. From this you can calculate 26. If you compare this L by D max and L by D provided, your L by D maximum is greater than L by D provided, so it is safe against the deflection, hence it's checked. So in the problem it was asked we have to check up to the deflection only. Okay, let me discuss this. This is the reinforcement detailing, right? So according to our design, we have to provide, as it is a one-way slab, we have to provide a main reinforcement along the shorter span. This is a LX direction, it is a LY direction. See, it is a main bar here and it is a main bar here. These alternate bars are cranked or bent. What is the bent? From the face of the support. So this is the support, this dotted line in the plan, it will show you the support. The dotted line is the face of the support. That would be 0.1 times L, a 0.1 times 3200, that will give the 320 mm this side and this side also. The bent length must be, this cranked length or bent length must be 320 mm, and alternate bars. In this alternate bars will be bent, here also alternate bars will be bent, and we have provided 10 mm bar, and the spacing we have to maintain it for 260 mm. We have what we have calculated, that is 10 mm diameter bar at 260 mm center to center spacing. This is about your main bars, and this is the distribution bars. There is no need of cranking it actually, and here we are providing distribution bar of 8 mm diameter, and spacing maintained for this bar is 280 mm center to center. So if I take the section here XX, if I cut the section here, if I see the cross section at XX, see that it will be look like this, and the main bars here, that black color straight line which will show you the main bars, and this is the bent bars with another type bent bars in the form of main bars, and these circles will showing you distribution bar, right? And that, see, the clear span between the slab is 300 mm, and this is the bent length of a bar that should be bent at a 0.1 L from the spacing. According to this problem, we'll get 320 mm. And this is the overall depth of the bar, that is 145, and if you take from the center to center of this bar, we'll get 120 mm is the effective depth of a slab. So these are the things what of today's lecture. So let me summarize what we discussed today. We have discussed what the design steps are. First of all, we have to assume the effective depth, then we have to calculate effective span of the slab, then calculate the total load which is acting on the slab. Based on the total load, I have to calculate what is the bending moment, maximum bending moment, and by equating the limiting moment of resistance and maximum bending moment, we have to calculate what is the limiting depth, required depth of slab, and the limiting effective depth of minimum required depth of slab should be compared with the provided depth. If the provided depth is more than the calculated depth, that is required minimum depth, then we adapt as a assumed depth for further proceedings. Then we have to calculate area of steel provided in the slab by using the Codal formula. Then we have to check with the Codal requirements. Then we have to go for checking of your deflection. Right. So that's all for today's lecture. Thank you.